All right, so previously we introduced if you have some function f of xy, or equally if you go f of xyz, or you could probably actually have more variables too, then we introduce this del of f, which is the gradient. So let's just do it in the two variable case. Del of f was the partial derivative of f with respect to x, comma, the partial derivative of f with respect to y, and it's this vector. And then eventually the goal is to be able to go backwards. If they give you del of f to go back to f. And our main tool before for going backwards, so backwards of vanilla differentiation, was integration, right, in one variable. And in order to do integration properly, or easily, we needed the fundamental theorem of calculus. So the fundamental theorem of line integrals is an analog of the fundamental theorem of calculus, but using line integrals and using the gradient. So if you have some curve C, we're going to say C is smooth. Smooth visually actually just literally means smooth. If it's super jaggedy, it's probably not smooth. Technically, it means infinitely differentiable. So you can take derivatives infinitely many times, and all those derivatives exist and are continuous. So that's the technical definition of smooth. But it really, visually, it's going to mean the same thing it means in real life, which is smooth. And then it's described by or parameterized by our position function, r of t, where t is between a and b. So if you have that, so C is a nice curve, basically, and then f is a nice function. F is differentiable, is nice enough. And actually, we're going to do one more thing. If we calculate the gradient on f, so it has to be differentiable, and the gradient has to be continuous, at least on the curve. It doesn't have to be continuous everywhere in the plane. So, you know, if here's our curve, then f could be badly behaved over here, and that's okay. We only care about on the curve. Then, so if 1 and 2, then we have that the integral of the gradient dotted with dr, the position function, is actually the original function evaluated at the endpoints subtracted. So this looks a lot like the vanilla fundamental theorem of calculus.